Welcome to Kaimak. My name is Godwin. In this tutorial section, we will look at how to design a dipole antenna at a resonating frequency of 2.5 GHz using HFSS. We will look at the antenna from theory before we start the design. From theory, this is how the dipole antenna looks like. It is like a wire or a pole which is separated by a gap, so we can look at this as a dipole leg to the beginning of the gap, and this is also another dipole leg. You will come across several formulas online which will show you how to calculate for this gap. If you are fortunate enough and you come across such formulas, it is okay, but if not, you can choose any appreciable length of the gap that won't temper with your design. And from theory, we know that the length of the dipole antenna should be 0.5 lambda, or lambda divided by 2. We will dive in the video and design our dipole antenna at 2.5 GHz. This is HFSS. I've named my project already, and I would choose a gap of 0.125 millimeters. 0.125 millimeters. I won't compute my gap with any formula, but our C is in meter per second, and our lambda is 0.125 meters as a result of C. So we will multiply our lambda by 1000, that is 120 millimeters. So our lambda is 120 millimeters. So we will calculate for the effective, I would say the effective length of our dipole. That is 0.5 times 120 millimeters. So we have 60 millimeters. 60 millimeters. So your 0.5 lambda is now equal to 60 millimeters with a gap of 0.125 millimeters. I think that will be okay and fine. It will work as well.
Audio jungle.
So I will select my cylinder, draw it along 0. I will rename it later. It should be on the origin. It's not compulsory, it can be anywhere, but I want it to be on the origin. And with the radius should be half of the gap. I will explain this later. So half of 0.12. Our calculator, we go for our calculator. Zero 0.5 times 0.125. So we get 0.0625 millimeters as our radius. So I will just input the value over here. 0.0625 millimeters, and the height is already 60 millimeters as we computed. This is what we have. I will pan so that we can see. It's very long. I will just reduce it. It has vanished. The thing is very long. Okay, so we have this. This is one thing I would do one thing because I can't see the full size. This is what I would do. This is the Z direction, so I would divide the 60 along the Z axis. In order for me to do this, I will take the negative of 60 and divide by 2. So I'll do negative of 60 divided by 2. I think this one should be okay. Yes. See that we have it's now okay. So we have some above the origin, that is in the positive Z direction, and some in the negative Z direction. So what we do is that we have our full length of the dipole and we don't know the gap. We would use a particular shortcut over here. We would just rename our cylinder. We'll call it dipole.
Audio Jungle.
Assign material to it. PEC is fine. After we assign our material, we will just copy this. We go to edit. We would copy. And paste. After pasting, when we select this, it is the same structure that it is highlighted. When we select that too, it is that same structure that is highlighted. The reason is that they have the same dimensions and directions, so they lie on each other. What we will do is that we would change the dimension, the height of this. We want the height of the second duplicated structure to be the height of our gap. So you get 0.125 for the gap, and we would make it divide the origin into 2. That is a midpoint. A midpoint should be between the gap. You would have the gap, some of the, like exactly half of the length of the gap above Z and some below Z. That is the origin, above the origin and some below the origin. In order for us to do this again, you do minus of 0.125 divided by 2. You would apply. When we now select this, see that it is selecting just a portion. So that is a gap that we've created over there. But when I don't select any of the structures, sorry, I need to change this to gap and the material from PEC to vacuum, because it is now serving as our gap instead of the structure. You see that we haven't just the structure. So what we will do is that we would subtract this from the actual structure, giving us the gap. But I don't want to do it in such a way that I would get just an empty space over there. So I would use something called the clone. So I will select both structures together, use the subtract, select clone two objects before operation. Then see that I just have to reduce the transparency of this one for you to see what I did. So we are having the cut through where we don't just have an empty space, it's like there is a transparent glass. That is what I was looking for. After this, what we'll do is that we would introduce our pot. The reason why I took the radius to be half the gap is that my pot would take one point of the circumference to the other point of the circumference, and if I want the radius, it should be half the length to the circumference, and I already had the gap, so the length of the gap is half that of what is twice that of the radius of the dipole. So I would introduce my pot. Before that, I just have to align it in a way that I won't keep long. Yes, this will be okay. I can zoom to get the best view. I will change. Okay, let me introduce the pot. We'll change the plane. SZ will be okay. Yes, this should be the right plane. Changing to YZ. Now introduce my pot. The same symbol that I used to start should be the same symbol I end with. That is, when I get to this, it changes. So it is okay. After drawing my pot, what I will do is that I will clear it and use the section. The reason why I would use the section is that sometimes we just want to adjust the parameters, and whenever I change the length, it will have a bad effect on this. So wherever that I make amends, the gap should also be amended. But when I do it in this form and leave it like that, whenever that the length of the dipole is changed, the gap won't be changed. So I will delete what I did. Delete, select the gap, go to modeler, surface, section, XYZ, press OK. I'm having it back. I will just change the name to pot. I will assign my citation lambda pot. Choose new line. Start from the bottom to the top. It is defined with no error.
Audio Jungle.
So I want to check and see if my citation is available. So the citation is available with no error. What we are left is with is the radiation box or the airspace. We will change to SZ. Rotate the structure in the axis. Or draw a box around it. Just any box. Name it air box. everything is fine, but we'll change the transparency so that I can align my antenna within it. Change the dimensions. The S size is any dimension is fine. You can choose 40. Y to be say 50. But since my antenna should lie within and the length of the antenna is 60, I can't choose a value which is less than 60, so I'll go for, let's say, 90 millimeters. So I want this to align directly on the board, so I'll take negative of 40 and divide by 2. I would also take negative of 50 and divide by 2. Take negative of 90 and divide by 2. After this, it should cover my structure, and my structure should line within perfectly. Yes, the antenna lines within perfectly. So you assign radiation to the box. Assign boundary. Radiation. We are down to check our radiation too. Everything is okay now. You will check our validation and see what we are left with. We are left with our analysis setup. So we go to analysis, add solution setup, choose advanced. This should be my resonating frequency, that is 2.5. Yes. Number of passes 10 should be okay. We will change our sweep type from interpolating to fast. I can start from 2 and end at 4. Step size of, let me change this from linear count to step. The step size of 0.02. This should be okay. I'm getting an error. Solve inside for object gap is set. Okay, I changed it to vacuum, so it shouldn't cause us any problem. So after this, I'll validate again and see everything is correct. So I can now simulate.
Audio Jungle.
The simulation is done. I think everything is normal. Normal completion of simulation and server. We had no error, so we go ahead and look at our results. So we plot our return loss. This is letter S parameter S11 and unit dB. Look at how our graph looks like. Alright, so this is the return loss. As I explained earlier, when we feed our antenna with the signal, we want to check the amount of loss that is incurred. This loss is a measure of the power that we input and that returns back. So we have a loss due to reflections at the port. So we have a standard, as I explained earlier, that is the -10 mark. Help helps to calculate the bandwidth of the device. So we trace the -10 where it cuts our graph. So it cuts our graph at this point. We can read from the x and y value over here. So we have 2.35, and the other side we have 2.49. So the bandwidth of the device will be 2.49 minus 2.35, and this point is the point where we will have the minimal error or the minimal return loss. This should have been on 2.5 because that is the resonating frequency, and the meaning of the resonating frequency is that the point or the frequency where our losses will be minimal. After the design is not perfect. We don't usually expect it to be on the 2.5, but it should be close. If you want it to be on the 2.5, you do something called optimization, which we will later look at it at the end of the last lesson. I'll go ahead and plot the voltage standing wave ratio. We plot it with no unit. So with the voltage standing wave ratio, I will change the scale. This is not what I'm looking for. My minimum should be 1. My maximum should be 5. With a spacing of 1. Spacing of 1. I hope this works. Good. So this is also the standard because we know the relation between VSWR and return loss. So if you want the bandwidth to, we will cross this, we would strike a line through the graph on the 2. We check, we have 2.34. This side too, we have 2.5. So 2.5 minus 2.34 will be the bandwidth of the device, and this point will be the point where we have minimal losses. After the voltage standing wave ratio, I already inserted my far field setup while I was running the simulation, so we can go ahead. This is it. I would like to take a look at it. There's it. Everything is okay. I will plot the H plane and the E plane. I'll start with the E plane. So I'll create far field report, radiation pattern. I'll plot gain phi together with gain theta unit dB. But the thing is, if I want to plot E plane, my principal axis should be theta, and the families, I won't plot all of phi. I will just plot 90 degrees of phi. This are E plane, it's an omnidirectional, so this is what we expect. This is the E plane, and these are unwanted radiations. We'll plot the H plane too as well. The H plane is like the E plane, just that with the H plane, our principal angle is now what? Phi. Sorry, it's now phi. We plot gain theta and gain phi together with a unit of dB. And once again, we change the families. We won't plot all of theta, just need 90 degrees of theta to cut through our 3D polar plot for us to see what the radiation. This is what we expect. These are unwanted radiations. I will go ahead and plot the 3D polar plot, far field report, 3D polar plot. I will check infinite sphere, gain total, dB. So these regions are regions where we have no radiation, that is the distribution of energy to this region, and underneath, let me show you, and underneath here is almost zero, approximately zero, but our design is not perfect, so I can't say it is equal to zero. It should be approximately zero. And this side shows the radiation patterns of the E plane, this side and this side, while this side shows the distribution of the H field. Thank you guys.